We're going to look at solenoids. And a solenoid is just a lot of wire wrapped around some central core. So this is an example of a solenoid right here. You can see that there are various wires floating along there. And then this is also a solenoid. And I don't know if you can see in the detail if it'll focus or not, but that's a whole bunch of wires, a lot skinnier wires than what we had before. I have some solenoid here. Current's going to flow, I'll have some current flowing in, some current flowing out, and so current is flowing throughout the whole thing. If I look at from an in point of view, I have basically a whole bunch of loops of wire here, and I have current flowing around one way or the other. It depends upon if, which side it's going in and which side it's going out. Let's see. All right. I think the current's going to be flowing that way. It really doesn't, not a whole lot of difference one way or the other. Since I have a current flowing around in a circle like that, it's going to produce a magnetic field that's coming out at us. A couple other things to point out, that if I have a whole bunch of wire with a current coming out, I'm basically looking at a cross section here. I have current coming out on top, and on the bottom it's going in. Each one of these wires is producing a magnetic field because the current creates magnetic field. And so for the wires on top, the magnetic field is going around counterclockwise. So if I look at just that one, it creates one going around like that. But it's not just localized to that, it spreads out. So, I got one going that way, and then one going that way. The wires down here also are creating a magnetic field. That current is flowing in, and so this one's going clockwise. Well, notice that these are vectors. They add like vectors. Inside, the magnetic fields are both in the same direction, so they add together. So my magnetic field in whole is going like that. There's my north side, my south side. External to the solenoid, when I'm outside the solenoid, we have some interference going on here, so the magnetic field is weakened. Now, if we look at some dimensions here, if we say that the length of the whole thing is L, and the diameter is D, if L is significantly larger than the diameter, it falls under the category of close enough to infinitely large. And if that's the case, then the magnetic field out here is practically zero. So outside the solenoid, the magnetic field is about zero. And out here, I guess they don't have, we'll just look at the magnitudes, that also works. I wrote newtons per coulomb, this Tesla. So all the magnetic field is inside. So what I'm going to do is I'm going to employ Ampere's law. Ampere's law states that if I add up the magnetic fields around a closed loop, that's going to be equal to mu naught times the enclosed current. Or from a calculus point of view, B dot dl around a closed loop is equal to mu naught times I enclosed. What I'm going to do is I'm going to draw a loop that basically covers a whole bunch of stuff. My loop is going to actually be a rectangle. So I've got a bunch of wires up here. Let's just take the top ones where my current is coming out. And I'm going to create a loop around capital N wires. Now the direction that I'm going to do my loop, I want it so that when the direction I go in the loop, if I use the right-hand rule, it should point in the direction of the current. In other words, since my current's coming out, I want to do my loop in that direction, in the counterclockwise direction, because my current's coming out here. So I'm going to do my loop in these directions right here. Since it's a closed loop, I need to start someplace and end someplace. So I'm going to start here. This is going to be side A, side little b, side C, and side D. And so this becomes BA dot delta LA plus B little b dot delta L little b plus BC dot delta LC plus big B little d dot delta LD is equal to mu naught times the current. Well, I've got capital N wire, so I have capital N times I. That is the total current that is enclosed here, because each wire that's inside has its own current. Now, dot product, remember dot product likes parallel. So my magnetic field that is created is practically zero out here. So remember that B is zero out here. And inside, B is not zero. But either way, my magnetic field is running to the right, just as I said up there. So along section A, my magnetic field is what I'm trying to find here. And my length is whatever length that is. And so why don't we make that length L? So that's BL plus. In this region right here, my magnetic field is either perpendicular to my length, because remember delta L, this is the direction of the current flow. So delta L is that way. It's either perpendicular or non-existent. Either way, this is zero, because dot products hate perpendicular. Along C, the magnetic field is zero. This is because B sub B is perpendicular to delta L sub B. And here, because B sub C is zero. And over here, again, perpendicular or non-existent. And so plus zero is equal to that. So we are now left with that BL is equal to mu naught capital N times I. If I divide by the length, I get B is equal to mu naught capital N over L times I. This right here is known as the coil density. It's the number of coils per unit length, and that's symbolized by a lowercase n. So this is mu naught Ni. So this is the ideal magnetic field at the center of a solenoid. And you can go through the complex calculations to find out what it is actually for a finite length and so on. But this is the magnetic field, magnitude of the magnetic field at the center of an ideal solenoid.